We're going to be going over lots of different concentration units. Some of these are review, and some of them are probably new. And there are a lot of them, so we're going to go through them one at a time. This is a long list. We're going to go through each of these. Some of them are more important than others. Molarity is by far the most important, which is why you learned that initially, first semester, and then we're going to go back over it now, and then we will use that a lot throughout the semester. The others are listed here as well. Molality, 3 different kinds of percent. Mole fraction should also be a review. Parts per million and parts per billion. And then we're going to review dilution calculations because I know that you did those some last semester as well. So let's start with molarity. Molarity is abbreviated with a capital M. The formula for molarity is moles of solute per liter of solution. The units are capital M, which if you're saying it out loud is molar, or you can leave it in the base units of moles per liter. We're going to start with a calculation, and we're going to do this together. Determine the molarity of chloride ion in a solution prepared by first dissolving 4.5 grams of sodium chloride in 40 mils of water, then adding 20 mils of 0.55 molar magnesium chloride, and finally diluting the entire solution to 125 milliliters with water. I picked this problem because I knew it would be challenging, so don't let that upset you. I'm sure that most of you could do a very simple calculation, but let's do this one together. If you can do this one, then you can do ones that are easier as well. Okay, so here's our problem. It's a good idea to start with the formula, moles of chloride per liter of solution. We have chloride from 2 different sources. We have 4.5 grams of sodium chloride, which sounds like a solid. And we also have 20 milliliters of 0.55 molar magnesium chloride. That's a second source of chloride ion. So we have to take both of those into account and add them together in the numerator. So moles of chloride from sodium chloride, we convert sodium chloride from grams to mole using the molecular weight or formula weight of sodium chloride. And we get 0.07700 moles of sodium chloride. Now you can see that the grams cancel, just like last semester, right? Dimensional analysis, the grams of sodium chloride cancels with grams on the bottom, and you're left with moles of sodium chloride. Now the second step, I'm converting moles of sodium chloride into moles of chloride, which you may be able to see very obviously as a 1-to-1 stoichiometry. So we end up with 0.07700 moles of chloride. That's from the first source. Now the magnesium chloride is a little bit different because it is a solution. So we have 0.55 moles of magnesium chloride per liter. That's molarity. It's a good idea to write that uppercase M that you're given in its base units of moles per liter. If you rewrite it in moles per liter, it's more obvious what to do with it. So what we're going to do with it is we're going to multiply it by the volume, which is 0.0200 liters. That comes from the 20 mils that you're given. I converted it into liters by moving the decimal over, 3 to the left, dividing by 1,000, same thing. Liters cancel, and we're left with 0.011 moles of magnesium chloride. Now here the stoichiometry is 2-to-1 because you can see that there are 2 chloride ions per 1 mole of magnesium chloride. 2 moles of chloride per 1 mole of magnesium chloride. So we have to multiply that number by 2, and that's going to give us 0.022 moles of chloride ion. We're going to add that to the other source of chloride, the sodium chloride. We're going to add those together. And that's in the numerator. You can see the 0.077 from the sodium chloride and the 0.022 from the magnesium chloride. Those go together in the numerator because we've just added them together, right? They're mixed in the same container. And then we're dividing by 0.1250 liters. And the reason we're doing that is because the total volume of the sample is 125 mils. The other volumes don't matter for this particular end of the calculation. So we get 0.792016427, way too many sig figs. So we're going to figure out how many sig figs we need. We went back to the previous slide just to check on sig figs. So I'm given 4.5 grams of sodium chloride. So I'm going to divide by, I'm going to underline the 5 there. And then that means that the 7 here is the least significant digit. And that's still over here. And then we're going to underline some other ones that seem important. So that means down here at the end, this 0.55 is the least significant digit there. And this second 0 is the least significant digit there, which means that we have 2 sig figs here and 2 sig figs in the final number there, 0.022. So that means that our two numbers on the next slide, that 7 is the least significant digit there, and the 2 is the least significant digit there. Now when we add them together, remember that the addition-subtraction rule says that when we add those two together, we end up getting 0.0990, and that 9 is the least significant digit there. So that number has 2 sig figs. 0.1250 has 4, and so our final answer needs to have 2. So this is my final answer, 0.79 molar. Now it might help to visualize what we're doing here. Okay, so we have some sodium chloride that we got out of the bottle, and we're just going to put that into our graduated cylinder. And we're going to add some water. There's our sodium chloride. We're going to add some water up to, what's the volume? 40 mils. Then we're going to take our second source, and we're going to add 20 mils of our magnesium chloride, which has our other source of chloride. And then at the end, we're going to dilute everything to 125 mils. And so it's that final volume that really matters in the denominator of our formula. So sometimes it helps people to visualize what's happening, right? We have moles from sodium chloride, we have some moles from magnesium chloride. We have to add those together in the numerator, and then we divide by the final volume, which is 125 milliliters. Okay, so we're going to check off molarity, and then we're going to move on to molality, which is probably new, but it's pretty important for this chapter. Molality is abbreviated with that lowercase m. The m is often italicized when it's in print, like it is here, but obviously if you're writing it by hand, you can't italicize it. So lowercase m counts for molality. Now, it's kind of important that you guys know that molality, lowercase m, a lot of you guys use lowercase m as an abbreviation for moles, which you've probably been told is wrong. This is the reason it's wrong, is because lowercase m means molality, so you shouldn't use this for moles. The formula for molality is moles of solute per kilogram of solvent, which sounds similar to the molarity formula, but you need to keep in mind that it is subtly different. Okay, the numerator is the same, but the denominator is different. It's a mass. It's also different because it's not the solution we're talking about, it's the solvent itself. The units are lowercase m, which if you're saying it out loud, you would say molal, or moles per kilogram. You can leave it in the base units if you wish. And we're going to do another calculation, determine the molality of sodium nitrate in a solution prepared by dissolving 23 grams of sodium nitrate in 425 grams of water. Okay, so we have our problem here with our formula. Remember, that's the first thing to do, is to write the formula. Molality is moles of solute per kilogram of solvent. Our solute in this case is sodium nitrate, and our solvent is water. Here we're going to determine the moles of sodium nitrate by dividing 23 grams of sodium nitrate by the molecular weight, which is 85 grams per mole. Or should I say formula weight, which is 85 grams per mole. Grams cancel. And we end up with moles of sodium nitrate, 0.270588. I'm going to keep lots of sig figs here. Now, we're going to convert this into kilograms because that's what our denominator needs to be. So 425 grams of water is 0.425 kilograms. I'm keeping that extra 0 there just to remind me that that number should have 4 sig figs. So you can either divide by 1,000 to convert grams to kilograms, or you can just move the decimal over 3 digits. So now when we complete our calculation, the molality of sodium nitrate is the numerator there, the moles we calculated. The denominator is the kilograms of solvent. And we end up with that long number, 0.636678201. Now, significant figures, all we've done is multiply and divide. And so the sig figs are pretty easy to calculate here. You look back in the original number, and you're given 23.0 grams, which has 3 sig figs, and 425.0 grams has 4, and so our answer should have 3. So we're rounding it to 0.637 molal. All right, so we're going to check off molarity and molality. We're going to move on to percent. We're going to do all 3 of those percents together. The W/W, the W stands for weight, and so that's a mass percent, which you learned about in Chem 101, but we're going to review it here. There's also a volume percent, which is the V/V. The last one there, percent W/V, is a weight volume percent. We're going to talk about all 3 of those together. They are similar, how they are different. So mass percent you learned about already. Volume percent is usually used when you have liquid solute and a liquid solvent, for example, ethanol and water. And a weight volume percent is used a lot in biology. For example, if you've ever run a 1% agarose gel, then that 1% signifies that you have 1 gram of agarose in 100 mils of water. So it's usually used when you have a solid solute and a liquid, and the solvent's always water. So the first one, the formulae for these, the first one is mass percent, where you have mass of solute in the numerator and the total mass of the solution in the denominator, multiplied by 100 to give a percent. The 2 masses should be in the same unit so that they cancel out. Now if we move on to volume, then the same is true here. The volume units should be the same so that they cancel out. They can both be milliliters, they can both be microliters, they can both be liters, they can both be gallons. As long as both of them cancel, then that's all that matters. Finally, weight volume percent is a little bit more specific. It's the mass of the solute in grams and the volume of water in milliliters. Now, the weight volume percent is kind of unusual because the mass and the volume, they really shouldn't cancel out, and we're going to talk more about why they are assumed to cancel out a little bit later. Okay, so we'll move on and talk about that, but the units for weight volume percent are also just percent. We assume that the grams and the mils cancel out. More on that later. Units for all are percent for all 3 of these. Sometimes it's indicated if it's a weight volume or a volume volume or a weight weight, and sometimes it's not indicated, it's just assumed based on the kind. Just depends. So that's what that top is saying. Which one is used is often specified, but is sometimes just implied. Liquid solutes dissolved in liquid solvents are often volume percents. We already mentioned that. Weight volume percents are often used when solids are dissolved in water to make very dilute aqueous solutions. Now the reason why that's important is because water has a density of about 1 gram per mil. And so then, therefore, the units sort of cancel if you have grams in the numerator and milliliters in the denominator. If it's an aqueous solution and it's very dilute, meaning that it's similar in properties to water, then those 2 units really sort of do cancel. Okay, so we're going to do this problem next. Determine the mass percent, volume percent, and weight volume percent of a solution prepared by mixing 10 milliliters of acetic acid. The formula is given there with 100 milliliters of water. The density of acetic acid is provided. The density of water is also provided. Here is our problem. We're going to start with mass percent. Mass percent is the mass of the solute divided by the total mass times 100. It's always a good idea to start with the formula. Acetic acid is my solute. And of course water is the solvent, and it's good to identify the solute and the solvent when you first begin. So I need to convert volume into mass using the density. Milliliters cancel, which gives me mass, grams of acetic acid. That's going to go in my numerator. That's 10.5. The total mass, remember, is the mass of the solvent plus the mass of the solute. So we need to add the mass of acetic acid and the mass of water. So next we need to calculate the mass of water from its volume and its density. Milliliters cancel, and that gives me grams. So finally I'm going to do 10.5 grams in the numerator, and I'm going to add 10.5 and 99.79 in the denominator. Those cancel, and that gives me a final answer of 9.520355%, which is way too many significant figures. So 10.5 should be 10.5. There it is. I'm underlining that at the top up here. And then 100.0 mils has 4, and 0.9979 has 4. In the denominator there, I added 10.5 and 99.79, which gives me 110.29. That has 4. So my final answer should have 3 significant figures, 9.52%. Now as we move on, we're going to do volume percent. Volume percent is the volume of the solute divided by the volume of the solution, the total, times 100. This should be easier because it's simply the volumes that were given. The numerator is 10, the denominator is the sum of those two volumes, 110.0 milliliters. Both of those numbers, the numerator has 4 significant figures, the denominator has 4 significant figures, which means my answer should have 4 as well because the number 100 is exact, does not influence my significant figures. And so my answer should be 9.091%. I have to round that O up to a 1 because of the 9. Now we're going to move on and do a weight volume percent. The weight volume percent is mass of solute divided by volume of water in milliliters times 100. So we calculated 10.5 grams of acetic acid in the very beginning when we did the mass percent. And we have 100 milliliters of water times 100 is going to give us 10.5% with 3 sig figs. Okay, so we can cross off all 3 percents. I'm going to move on to mole fraction. Mole fraction has the abbreviation with that weird looking, looks almost like an X. That's a Greek letter. That's the lowercase Greek letter chi. The formula for mole fraction is shown here, where mole fraction equals moles of solute divided by total moles, and that would be moles of solute plus moles of solvent. You would have learned mole fraction last semester in Chem 101 when you learned about gas laws. This is related to the law of partial pressures, where the partial pressure of a gas is equal to the mole fraction of that gas times the total pressure. So this is review, but we're going to go over it again. Mole fraction is a fraction, which means it comes out of 1. And so rather than a percent, which is out of 100, this is out of 1. So the possible values for mole fraction range from 0, if there is none of that solute in the mixture, up to a possible of 1, which would mean it is a pure, sample, not a mixture. The units for mole fraction, there are no units because moles in the numerator cancels with moles in the denominator, and therefore it is a unitless value. We're going to finish with a new calculation, determine the mole fraction of iodine, I2, in a solution made by dissolving 2.5 of iodine in 20 grams of benzene, which the formula is given there, C6H6. Here's our calculation for mole fraction. Determine the mole fraction of iodine in a solution made by dissolving 2.50 grams of I2 in 20 grams of benzene, C6H6. Again, it's a good idea to start with the formula. Mole fraction of I2 equals N, that's moles of I2, divided by N total. Here we're converting grams of iodine into moles using the molecular weight of I2. Grams cancels, and that gives us moles. And then the total moles is going to be moles of solute plus moles of solvent. So we need to calculate moles of benzene, and we need to add that to the moles of iodine. So moles of benzene, we're going to start with 20 grams of benzene, which is given in the problem. And we're going to divide that by the molecular weight of benzene, 78.108. Grams cancel, and that gives me moles of benzene. to finish, we're going to plug those into the original equation. So we have our numerator, 0.009850276 moles, divided by the denominator, which is the sum of the moles of iodine plus the moles of benzene. Try to get rid of that bar that I put on there. There it is, and 0.038469. The underlined blue is my significant figures. It appears that everything has 3, and so we're going to have 0.0835 as our final answer. Now we can cross off mole fraction, and we're going to do parts per million and parts per billion together because they are very similar. So ppm and ppb, those are the abbreviations. The formula are given here: mass of the solute divided by mass of the solution. For parts per million, you multiply by 10 to the 6th. For parts per billion, you multiply by 10 to the 9, which is a billion. This is similar to percent, except that instead of multiplying by 100, you multiply by a million or a billion. Those mass units, just like percent, cancel out. That's true for both of them. The units are either ppm or ppb, depending on which one you're calculating. These are typically used for very low concentrations. We're going to do this calculation, calculate the concentration in parts per billion of lead ion in a sample of contaminated river water if 1.0 kilogram of river water contains 19.6 micrograms of lead ion. We're going to start with the formula for parts per billion, which is given there: mass of my solute, which is lead ion, divided by the mass of the solution, times a billion, right? I'm going to plug those numbers in, but we need to convert them so that they are the same unit. 19.6 micrograms, we're going to convert them both into grams just to be easy. Divide by 10 to the 6th micrograms per gram, and you get that number. We take 1 kilogram, multiply by 1,000 to give us 1,000 grams. And then we're going to plug them in. Now it is conceivable the mass of the solution is really the river water, which is why it's 1,000 grams. That's not really the solvent, although the solvent, the mass of that solute wouldn't change the mass of the solvent anyway. But that is the solution. The river water itself is the solution. So we plug those in. We get 19.6 parts per billion. And that's just to let you know that 19.6 micrograms, this has 2 sig figs in the ends, so it's really 20 parts per billion. We finished all the different examples of concentration units, and the last thing I wanted to do was to review dilution calculations. This is something you almost certainly did last semester, but I want to make sure everybody knows how because it's really important. Now in a dilution you have a solution. The one on the left in my cartoon is a stock solution, so it's a very concentrated solution. And in a dilution, I'm going to take a portion of that out, whatever volume I take out, and I'm going to put it in a new container like you see here. Then I'm going to dilute the container on the right with just pure solvent. So the moles of my solute that I put into the new container is just the molarity of the solution on the left times the volume that I put into that container. Right, molarity is moles per liter. If I multiply that by liters, that gives me moles. Now I'm going to take that new solution and I'm going to dilute it with solvent. So the moles of solute that I originally put in there, M1 times V1, that is the same as the molarity times volume on the right-hand side, M2 times V2. So we have a new molarity, which should be lower, it should be more dilute, so it's a lower concentration than the solution that I originally had. And remember, molarity times volume is going to give me moles again. So because the moles that I put into that container before, it should be the same as the moles that are in there now, right? If you count up the number of little red spheres, on the left I have 1, 2, 3, 4, 5, 6, 7, 8, and on the right I have 1, 2, 3, 4, 5, 6, 7, 8. Because I only diluted it with solvent, I haven't added any solute. And so that's why we get the equation we get, which is M1 times V1 equals M2 times V2. The M1 times V1 is the moles that I calculate from the left, the moles of solute that I put into that container. And it's the same number of moles of solute, that's why they're equal to each other. And that equals the new molarity on the right times the new volume. We'll do this calculation as an example. Calculate the volume in milliliters of 0.55 molar sodium chloride required to make 150 milliliters of a 0.0025 molar sodium chloride solution. Alright, so here's our dilution problem. This should seem shockingly easy compared to the other ones that we've just done. Here's the formula, M1 times V1 equals M2 times V2. You just need to identify which one is M1, which one's M2, and all that. So there I've plugged in M1 is 0.55 molar. I'm trying to figure out what volume of that solution to dilute to give the resulting solution, which is M2 and V2. And then we solve for V1, and we do that this way. The two molarity units cancel, and that will give us milliliters. And now we have 0.68181818, and that goes on and on forever. Significant figure-wise, looks like we have two significant figures in this number and two significant figures in 0.55. 150.0 has 4, which means that our final answer will just have 2. So it's going to be 0.68 milliliters. Now another good verification here is that the volume of the concentrated solution that we need should be much smaller than the total volume of our new diluted solution, right? This is the volume of stock solution that we need to remove in order to get our final solution. So that's my final answer.